Hello, my name is Shah Mokshat, and today we are discussing about the CWS project under the course of Fundamentals of AI. So, the name of the project is a stock prediction using neural network, LSTM, and transformers. So, basically, we are using different models for the stock price predictions, and so yeah. So first of all, let us understand the problem. So in the stock market, there is extremely a volatility, and there are many features and the factors which influence the market simultaneously at a time, and it makes an accurate making an accurate prediction become challenging for human actually. So yeah, that's a problem. Another thing is that humans are naturally biased over some stocks, maybe because of their own country or because of some emotional bias, and also because of the limited information or having a limited data gathering capacity. And because of this reason, we also increase the risk uh, in investment and also do inaccurate forecasts. And the traditional techniques are having lack of adaptability over new changes in the market, and also often fail to provide a correct prediction because of that, because the market is continuously changing. There are continuously new technologies coming. Because of that reason, the traditional method over and over again uh, don't gather up much information, and because of that they are becoming outdated for reason of that. So for this we have a solution that we can make a data driven model, and we can make on such a scale that it makes the accurate prediction for the stock price over a short period and a long period predictions. um, Another thing is we can also minimize the human bias over the predictions, as the model doesn't have any emotional bias and all, and also make reduce the risk and also reduce the inconsistency in forecast. Basically, model will be more consistent in predicting the correct price for the stocks, and also the model will adapt to the rapid market changes, and because of that we can have a good hold over the prediction of the short term and the long term prices in the horizons. So yeah. So our objective in this project is that we build a machine learning and deep learning models to forecast the stock prices, and based on the historical and the financial data. Basically, we have a data set of having a more than 2,500 companies and with 29 features. Generally, it includes some kind of ratios, asset turnover, or there are like debt by equity ratios and all kind of features which makes the company having which can give the sufficient information about the company and how it is growing. We can have a quick ratios, we can have a cash ratios, and this type of features we'll be discussing in this project. And this model will predict after a year, 2 year and a 3 year of a price of a particular company, and we will check the performance of all these models using a metric called RMSE, root mean square error. And as we all know that lower the root mean square error, more good will be the product, more good will be the model. And we will also see that which model is more consistent and accurate in stock price forecast along the different time horizons. So basically, let us give a data set overview. So as I said, it having a historical stock market and financial records over the multiple companies, something around more than 2,500 companies, and we have total 29 features of each companies, and total there are something around 29,000 rows of the data, and the features include PE ratios, earning per shares, revenue, market cap, and many other stuff like, as I said, asset turnover, then uh, maybe a revenue turnover, all this type of inventory turnover, this type of features are given in the along with the companies. And yeah, this is overall the data set overview. And yeah, the target variables are stock prices for the year 1, 2 and year 3. So we will basically predict the stock prices for after a year, after a 2 year, or after 3 year. Basically a short term investments and mid term investment and long term investments. So yeah, this is a data set statistics. The number of variables are 33. The observations are something around, as I said, 24,000 around. The missing cells are quite high. We will do something about this in a later presentation. Uh, something there are no duplicate rows, and yeah, the numeric variable types are 24 and the text variable types are 9. So first of all, we will do data pre-processing before jumping into the model and the training of model, because without perfect data, the model will not give good predictions over that. Like we have to first handle the missing values. All the missing values are being removed or being replaced by the mean or something else. Okay, we will discuss out there how we removed and how we had added. Generally, we use the company's mean, not a global mean, to handle the missing values. Then we had treated the outliers. So the outliers are the one which is far away from the mean and the median. So sometimes it's a noise or exceptions. So we have to handle also that. We cannot remove, or we can also remove by using a Winsorization. And yeah, because that will create an bad training model. It will basically inter interact with the normal data, and it can create some kind of what to say, a bad model train. Then we normalize the data, as we know that some features are of a scale 1 to 10, and some features are maybe from 0 to 10,000. So for the model, it is difficult to work with a different scales. So we will try to make each and every data on a same scale, basically between the 0 to 1 or -1 to 1, which will be seen forward. Then we will split the data into train and test. Generally, we use 20 to 30% data into the testing and 70% data into training. Okay. So let us see the code for data pre-processing. So this is a code for a data pre-processing, and as you see, first of all, we have gather out some information. This is above top 5 datas of the company. As you can see, there are total 29 features, 3 target variables, then a year and a company. This is info. As you can see, there are much missing values over the columns, and this is mean, the standard deviation for each and every columns and the row. This is not much useful information for a while now, but still we have taken it out. So now we will start to basically fill the missing values. Okay, so first of all, we will convert convert into this type of column, the target 1, target 2, target 3 into strings, and then we will remove that. And also we will sort this data by time. Okay, because of some models will require time sequencing, which will I will explain in next. um, so yeah, we will using target 1, target 2, target 3 as our target variables. Then we will try to fill the missing values. So basically, as you can see, we use a company mean and a global mean together to fill the missing values, because it will be more accurate if some data of a particular company is missing. So it would be more accurate if we use the company's data to fill that mean along with the global mean. So that's what our motivation is here. And so this is how we had filled the missing values using company's mean and a global mean. And yeah, at last we do not have any null values over here. Actually, we don't remove any rows, we add the mean values. So yeah, the data is not being reduced, it's the same previously. Then we will also handle outliers. For outliers, we use the Winsorization method, and we kept the values outside the IQR bounds. Basically, uh, uh, 1.5 into IQR. IQR is Q3 minus Q1. Basically, 75 percentiles data and the 25 percentiles data. We subtract it, and the value which we get, we multiply with 1.5. We subtract from the Q1 and we add into the Q3, and the last data which we get from that value is being replaced to the above and the below of the value. For example, all the above of the Q1 values are being replaced by the 1.5 IQR value, about Q1 minus 1.5 into IQR value, and the all the below value of the Q3 plus 1.5 into IQR is being replaced by the 1.5 IQR. Okay, so yeah, this is how we kept the outliers generally. So we had also normalized this data, and then we had standardized the data into the 0 and 1 format, and at last we will get a clean data sheet. So moving to the PPT again. So yeah, first of all, we have done the data pre-processing, and now we can easily go to the model training. So here we use four kinds of model. First of all is multi-layer perceptron. Second is a long short-term memory, LSTM. Another, the third one is basically we are adding a attention layer over the LSTM, and we will see quite significant result after that. We will explain this. I will explain this. And the fourth one is transformer. So first of all, let us discuss about the multi-layer perceptron. So multi-layer perceptron, basically it's like you can say it copied from the architecture of our brain. It basically works like how the neural network in our brain works. Okay, so multi-layer perceptron is a multi-layer perceptron. You can say it's a fully connected neural network and feed forward neural network. And since we probably uh, discuss the data pre-processing, we can move towards the understanding the architecture of the MLP. So first of all, the core structure of the MLP is a feed forward network in which there is an input layer, uh, another is a hidden layer, and there is an output layer. The hidden layer is considered as a brain of an MLP, and all are fully connected, and from one layer to another layer there are weights which being attached with an input node. So first of all, input layer receives the raw data which we will give, and it is not doing any computation. Okay, and node count is determined by the number of features in the input data. It's very simple, like if we have 29 features on which we have to work, we will use 29 nodes. Okay, then we come to the hidden layer. It's a complex network, and yeah, it's considered to be as a brain, and it's a like hyperparameter is chosen by the user itself. If you use more nodes, more will be the computation, and you can say more accurate the prediction will be. But because of the more computation, you have to balance with the nodes. You cannot take the thousands of nodes and just use their architecture. You have to see how the nodes will work, and after that, after the moving from the hidden layer, we have an output layer. It will produce a final network prediction or a result. Okay, so let us go to the detail of it. So first of all, let us talk about the weight. So the weight is between the each connection between the two neurons, and basically it represents the strength or the weight of the feature used to predict the particular data, like how much the particular feature is important or less important. It is being decided by the weights. And it can be considered as a primary parameters the network learns during the training process. And let us talk about the another term, that is biasness. So basically the biasness is an independent constant we add with the weighted sum in each neuron, because biasness allows the activation function to be shifted from the 0 comma 0, because in each of the node there is an activation function. Generally we use a ReLU function. So what happened is, if we don't use the biasness, then it will go from the origin, and all the nodes will go from the origin, then we cannot get the correct predictions. So to get a correct and a clean prediction, we use the biasness as a constant, and we add with the summation of the weights of nodes. So yeah, this is how the neural network been calculated. You can see the maths over here. So this is an input vector, input layer in which these features are being added. Then there is a hidden layer in which we add a weight over the feature and the biasness, and then it is then gone to the ReLU function. The ReLU function then compute the value, and then we have an output layer. So this is called as an activation function. So activation function is then used as a processing. So it is a most critical feature of an MLP. Um, it can detect the non-linear patterns. Generally, previously we only read about the linear regression and all stuff. They only predict the linear type of patterns, but with the help of MLP and with the help of this activation function, we can also predict the non-linear patterns, which are generally unpredictable by even human intelligence. So yeah, we use the activation function for that. So yeah, that all has been done in the hidden layer. So after activation function gives the output, it goes to the output, and we get a predicted value in the output layer itself. As you can see, this is the equation of the output layer. And generally the hidden layer, um, generally after the output layer, it gives the sigmoid, it gives the binary classification between 0 and 1, and then we scale up to our features and we get the correct predictions. This is our training the MLP, in which we use the loss function. It quantifies the error on the predicted value and actual value, and that error we again give to the neural network. This is called as a back propagation, and with the help of this error, it continuously changing its prediction and being more, you can say, more predictable, or making try to make a less error or something like that. It is a repeating process. Again and again we give an error to the uh, network, and the number of times we you do this process known as an epoch. More epoch, more will be the less will be the loss data, less will be the error, but of course more will be the computation. So generally we use 1,000 epochs in our data set, and after that we optimize that loss function, and at last we get a prediction from the model. Let us see the code of the uh, MLP. So yeah, this is a basic code, and yeah, these are the outliers, how we handle it. Okay, so here we had trained the MLP mode. We use the torch NumPy and the pandas for this code, and we use at least 1000 epochs for training. This is the code, you can just see. This how the back propagation works, and the loss function is continuously decreasing, as you can see. As you can see how the training loss versus epoch graph is being shown, as I had seen that error is continuously decreasing as the epoch is growing. And then we have done training and we calculated RMSE. So RMSE is quite high for the MLP. That is a target one, it is 107, target 2 is 206, and 376 for the target 3. We will see why it is like this. There are the reasons why there is such a high RMSE, and we will not get much RMSE over the next models. These are the predicted target 1 versus actual target 1 graph, as you can see. And these are the shape values, that which features has more importance in the training. You can see that sharp interaction value. So yeah, this is the test scores and the predicted data. So as I've seen that MLP cannot capture the time dependency and the sequential patterns present in the stock data. Basically it tells about that the stock price is more relevant if it is more recent over the times. So for the MLP, each and every data is equal in the sense. Because of that reason, in the stock prediction, MLP cannot be used or can be less used, because we have to give more weightage to the recent data. There's more time dependence in sequential data, which the more advanced models like LSTM and the transformer can do easily. And also it can overfit on the trained data and can get a low error accuracy in over the test data. And also it requires, as I say, predefined input length over the input layer and the hidden layer. And it cannot handle the variable length sequences, as if some kind of prediction require more length sequence, then it cannot handle. So because of that reason, in some values it is very absurdly predicted. Now moving on to the LSTM. So first of all, let us understand the architecture of the LSTM. So LSTM basically having a long short-term memory. So is specialized type of recurrent neural network, while the as you see, the general purpose of MLP was a foundation of many deep learning models. Even the LSTM is, but the LSTM is specially designed to handle the sequential data, and it's more good to handle the time variant and the time dependent data, and also address the vanishing gradient descent problem, as you know that how the information is being vanished over the time, and it is very good architecture over understanding the this kind of problems. And also this problem was basically over the traditional RL network. And so the core component of the LSTM is a current input, previous hidden state, previous cell state. So basically the current input is a data point which you provide on the current state, and the previous hidden state is basically this is a short-term memory and the output of the previous LSTM. Okay, and the previous cell state, and this is kind of a long-term memory, and which runs through the entire chain and has a minimal interaction, so make it easy for the information to flow unchanged. Okay, so basically LSTM updates the hidden state and update the cell state. The architecture is defined by the three gate, as you can see. One is forget gate, input gate, and the output gate. The forget gate decide what information to throw away from the old cell state. It takes the current input and the previous hidden state. It outputs a vector of value 0 to 1 via sigmoid function. Okay, as you can see, the sigmoid function. So basically, it throws away the long old information and try to gather up the previous short information, like recent information, and it outputs a vector between 0 and 1 because of the sigmoid function. Okay, and then it is multiplied by the cell state, filtering out the irrelevant information. And then it comes to the input gate. Input gate decides the what new information to store in the cell state. This involves two parts. First of all, there is a input gate layer and the candidate layer. First of all, let us understand what the input layer gate layer do. So input sigmoid layer decides which new values to update, how much new information is important, and the candidate layer, the 10H layer, you can say, creates a vector of a new candidate value, and it basically squashes the values between -1 and 1. So it is the use of the candidate layer, as you can see, the 10H function and the sigmoid function. Okay, then we go to updating the cell state. Basically, the old state is updated to the new cell state, and the combining the forget decision and the input decision overall. And at last, the output gate. The output gate decide what part of the cell state will be used to generate the hidden state. Okay, and this time the hidden state is also the output of the LSTM. So the sigmoid layer decide which part of the cell state, which is the new cell state, to output, and which part of this cell state want to go to the hidden state. Here also the tenants cautious the cell state, and this is how we get the hidden state and the cell state of the current prediction, and this is how the LSTM works. So moving on to the predictions. This is a code over the LSTM. Here we use 200 epochs, which is quite low for the LSTM, but yeah, we can go through with it. As you can see, these are the charts between predicted target and the actual targets, and these are the RLC score. It is quite lower than the MLP, as I already said, because LSTMs are good at sequencing data and the time dependent data. Because of that reason, it gives more weight to the recent data rather than the previous data, and because of that reason, we are getting more accurate prediction than MLP. Now moving forward to the limitations of the LSTM, it is slower due to sequential processing of the time steps, and but still it reduced compared to RNN, and still possible for very long sequences. Performance is very sensitive to the layer size and sequencing length and learning rate. So now let us talk about the LSTM plus attention layer. Now we will use the attention layer with the LSTM. So combination of long short-term LSTM and with an attention mechanism create a better architecture, and particularly for the sequence to sequence tasks, like for example you can say machine translation or a text summarization. The limitation of LSTM was that it need to compress the entire input sequence into the single fixed context vector, as we had talked about the 10H functions, and which often leads to the information loss. Of course, if you have much more large data, and if you squash to the minus and one, it is possible that you are losing some information over it, and especially for long sequences. And okay, So this explanation builds on a capability of a LSTM to retain and regulate the information over a long sequences using the internal gate and the cell gate. Okay, and moving to the how LSTM attention works. So basically, as you can see here in the architecture, attention mechanism usually implemented in the encoder hidden states and allows the model to dynamically focus on the most relevant part of the input sequence at each time of generating output sequence. The encoder, like the input processing, the LSTM encoder process the entire input signal one step at a time. Um, the hidden state at each time step, the encoder produces a hidden state H. The collection of all hidden state essentially contains the contextual information for every part of the input. Okay, so the entire set of hidden states is passed to the decoder and then decoder generates the output sequence one token at a time. At each decoding step, the decoder LSTM produces its own hidden state, which summarizes the information generated so far. Okay, so the calculate attention score. This the like they also calculate the attention score, and this kind of scoring function like a dot product or maybe content based or an additive is used to compare the current decoder hidden state against all the encoder hidden state. The result in a set of attention score for every encoder state. Okay, they also calculate the attention weights. Then scores are normalized using a softmax function, as sir you already discussed with us in the class, the softmax function. And these weights are then probability distribution indicating how much focus should be placed on each input state to predict the current output token. This is the most important part of this architecture, as you note. And then the context vector is being calculated as the weighted sum of the encoder hidden state using the attention weights. This CT is a dynamic summary of the specially tailored for the current decoding state. Then we go to the generate output. The context vector is combined with the current decoder hidden state to create a new vector. This new vector then fed through the output layer to predict the next output token. And the new hidden state is also passed to the next decoding state. And this is how we predict the current state. And again we will back propagating this architecture using the epoch. Okay, so let us see how the code works. So this is a code for the LSTM with attention layer. As you have seen, this is the code for the only LSTM. And yeah, we have used 2000 epochs for this layer because it is a most important model, and there are many results from this model will be coming out. As you see the graph, as the epochs increasing, the training loss decreases. Okay, so these are the predicted value, the target 1 versus target 2. As you can see from the graph also, much more correlated prediction is being shown within predicted data and the actual data. As you can see, the target 1 is quite low from the LSTM. It is just 24. The target 2 is also much low from the LSTM, and the target 3 also much low. So yeah, let us talk about the limitation of it. It's not much limitation, I guess, say, because this just that it raises the computation time and the memory usage. More parameters are being used, so there are chances that the data can be overfitted over the small data set, of course, not in the large data set. And it's also sensitive to initialization and learning rate scheduling. So now let us move towards the transformer. So the transformers architecture is quite complicated. I will try to make you understand in a much simpler language. Let us understood. So okay. So first of all, it is not related to. First of all, it is not related to any other architectures we had seen before it. It is totally the new architecture, and let us understand with the image shown here. So the core architecture of the transformer is that it comes from the disk, as we had already discussed in the class, the paper about the attention is all you need. So it's follow basically the encoder and decoder structure. Though the encoder block, as you can see here, the encoder block is to map an input sequence of a symbol to a sequence of a continuous representation. It is typically a stack of n identical layers. Okay, so basically each encoder layer has two main subcomponents: the multi-head self-attention and the you can say the position-wise feed-forward network. Okay, so what these multi-head, first of all, we talk about the multi-head self-attention mechanism. It allows a word to look at all other tokens in the same input sequence to compute a new representation that incorporate context. For example, for the word bank, it can determine if it refers to a river bank or a financial bank based on the word in the sentences. Okay, so basically it also see other words to make a guess for a single word. It uses a mathematical concept called a scale dot product attention to calculate the importance for attention score. Basically, it vectorize each and every word, and on the basis of the vector, it sees the different words is being, how the different word is related to this word, and how this different word from the sentences is related to this. Okay, so this model runs on the self attention mechanism. It doesn't need any required outside attention layer as we have to give to the LSTM. It has a self attention mechanism, and yeah, also represent different subspaces. Focuses one attention focuses on grammar, another on the meaning. That's how the attention system works. Then moving to the feed forward network, it's a fully connected, of course, a neural network, and it's independently and identically to each position in the sequence. It is served to refine the contextual information gathered by the self attention layer. Okay, then first encoder layer have a couple steps: token embedding, the position encoding, uh, like the input tokens are converted to dense vector, as I said. Since the transformer are process all the tokens in the parallel, it loses the information about the word order. Okay, so often sinusoidal values is added into each token embedding the inject this crucial personal information, positional information. Then come to the decoder block, as we have covered the encoder block. Now moving forward to the decoder block. So decoder block role is to take encoder's output and they generate the output sequence. Basically it converts the vector to the word, okay, or the some other kind of predictions. You can use the transformer in each and every case, even in the image, even in the which we have used like in the data set. It's not like that we have to use only in the text based data. Okay, you can use anywhere the transformer. That architecture is mainly focused on the text data. That is a different thing. Okay, so now let us go to the decoder. Each decoder has a three main layers: mask multi-head self, like self attention, like you will see multi-head self attention, mask multi-head self attention. Then it's multi-head cross, okay, and then position wise feed. There are three layers in which how it works. So both the key structural element for the transformer is both encoder and decoder blocks used to key structural techniques that aid the training stability and convergence. Okay, layer normalization, residual connections, these are the key elements which is being used. So this is the transformer architecture. So now let us move towards the code. This is the transformer code. We have used nearly 1,000 epochs for the training of data in the transformer model. As you can see, this is the code for the transformer. This is a training versus loss epoch. It increased, then it decreased quite well. So as you can see, the target 1, predicted target 1 and actual target 1, predicted target 2 and actual target 2, predicted target 3 and actual target 3. The RMS score for the target 1 is quite high. From the LSTM plus attention, the transformer is used for the large data sets and for the long range data, for the more data. So it works quite well with a more complicated data, or you can say more informed data, but not works quite well with a short data or not so long data. So because of that reason, we are getting higher RMS score than LSTM plus attention. But for the target 2 and target 3, because they are long-term predictions, we use more computational power, more neural network. On that, transformer work quite well than the LSTM plus attention. The limitation of transformer, as I discussed, it underperform on the smaller sets, but again it quite perform well on the larger sets. It more computational powered, and yeah, it has much memory complexity, and because of that we use the more computational energy. And it hard to explain that which feature is being used more to predict the particular data. We cannot find in the transformer architecture. So now let's come to the conclusion. So as you think that the MLP has the highest RMS score and it's unreliable model for the stock prediction, we cannot use the MLP multi-layer perceptron for the stock prediction, as because it cannot capture the temporal dependency in the stock data, and it's not used for the time sequences. LSTM work quite well for than the MLP, but still it is not the best, you can say, model to use. It's because the help in model time dependency effectively. Okay, but when we use attention layer with the LSTM, it works quite well, because now we are focusing more on the past time data, that which time of data is used more for the prediction of the data. Because of that reason, LSTM plus attention is quite working well than the LSTM itself. Then we use the transformer. The transformer gives outperform all the models for year 2 and year 3, but not have a higher RMSE for the year 1. In the year 1, LSTM has the lowest RMSE, and because of that reason we came to conclusion that the for a smaller sets, LSTM plus attention quite works well than the transformer, and for the larger set the transformer outperform each and every neural network models, even the LSTM plus attention layer. So yeah, this transformer self attention and captures the long range dependency effectively, but it may need more data to generalize well for short horizons. Okay, so this was a conclusion, and yeah, we have developed the model. We have actually tested all 4 models on the data set, and at last we came to conclusion for that the transformer worked quite well for the year 2 and 3, and the for year 1 the LSTM plus attention was the best model out of 4. So yeah, that's it, and thank you for time. Thank you.